This is problem 64 from chapter 2. 64. This is not one of the easiest problems, but I thought it might be interesting to take a look. A ball is dropped from the top of a 50-meter high cliff. At the same time, a carefully aimed stone is thrown straight up from the bottom of the cliff at a speed of 24 meters per second. The stone and ball collide partway up. How far above the base of the cliff does this happen? Okay, so we have a cliff, 50 meters, and we throw something, and at the same time we throw something up. Now, the first things first, we have to choose a coordinate system, and I'm going to make the traditional choice. I'll choose ground as 0 and up as positive for my x-axis. This is just, the first one is just drop, the second one is V0, 24 meters per second, and they collide somehow, and they're asking at the time of collision, what's the height? What's the height of the collision? Okay, how far above the base of the cliff, right? So just the coordinate of that point is going to be our answer in this case. Now, how would you solve this problem? What happens at the time of collision? Now, at the time of collision, their positions are the same. So the first thing that comes to my mind is to write down the positions for two of these objects, and then set them equal to each other and see if I can solve for the height. Now, I can't do this directly. Now, typically in these problems, when they're not asking about time, then you will just use the timeless formula, v squared equals v0 squared plus 2a delta x, something like this. And they're not asking about time, but we don't have anything about their velocities. Okay? And we know the initial velocities, but we don't know anything about their velocities, so this is not going to give us, if you write this formula, this is not going to give us something usable, because we are not going to be able to solve for delta x, that we are going to have two unknowns. So even though this might be the first thing that comes to your mind, this is not going to work, but we can actually use the clue. We can use the clue that they're at the same position. So I can write down the position formula for both, and then figure out a way to solve them simultaneously. That's of course going to involve time, so it's not going to be solved in one step, maybe multiple steps. But let's write down, so the one that's dropped is the ball, so x ball is x0 ball plus v0 ball delta t plus 1/2 a ball delta t squared. Okay. Now for the rock, x rock is x0 rock plus v0 rock delta t plus 1/2 a rock delta t squared. Now, a ball and a rock, they are both equal to gravitational acceleration. They're both equal to minus 9.8 meters per second square. One is moving up, the other one is moving down. Doesn't matter. I chose up as positive. Gravitational acceleration is down. The accelerations are both going to be negative 9.8. Let's write this down here. AB is equal to AR is equal to minus 9.8. Okay. Meters per second square, of course. Now, can we set these equal to each other? What do I know? For the ball, this is 0. Okay. And this one is going to be 50. The ball, this one is 0. This one is 24. And I know the accelerations. It's minus 9.8 both cases. I'll set these equal to each other, and then solve for delta t. Now, it might look like that you're going to get a quadratic in this case, but you don't, because the quadratic term are actually going to cancel with each other. I set this equal to that. I'm going to get a complete cancellation. And in fact, I can write for delta t. Delta t is going to be minus x0b over v0r. Right? I set these equal to each other. Sorry, there is no minus. They are equal to each other. Does this make sense? 50 equals to this, 0r. Yeah, so they are both positive. My delta t is going to be positive. Now, this is an accident. Okay, you actually have to write this. I mean, the simplicity of this formula is an accident. You actually have to write this, and then set these two equal to each other, do the cancellation, and solve it that way. You could make this more complicated. This could be similar to problem 66, where the throw times were not equal, so you wouldn't get this cancellation between these two terms. This delta t could stand for different things. So I have a video on problem 66 as well. Check that out to understand what I mean. But writing this directly is not good. You actually have to write this and get that result. So, but you can almost calculate this, right? This is not 2, but maybe 2.1, 2.09, 2.08, something like that. Okay, I mean, you use your calculator. I don't want to go through this, but this is your delta t. Now, once you find delta t, they're not asking for the time, they're asking for the height. You have to substitute this in. I think it's easier to substitute here. There's only one term with delta t here. It's 50 plus, minus 1/2, 9.8, 50 by 24 squared. And that will be the height, that will be the position of the ball when the collision occurred, and that's going to be the height because we chose the base of the cliff as our origin as 0. Now what does this look like graphically? Let's also do that one. Okay. So x versus t. The ball, let's do this with red, starts from 50 and drops down, okay, as a parabola. Its initial velocity is 0, so this is the tip of the top of the parabola. Whereas for the rock, this is going to be drawn up, so they collide, somewhere here. This will be our h. Graphically, it looks like this. So now I'm more confident that I did this correctly, that I get a single solution because these are going to intersect a single point. Okay, these two parabolas. Parabolas can intersect at multitude of points. When their axes are parallel, they can intersect at 0, 1, or 2 points. These are going to intersect at a single point, okay, because of the geometry of the parabolas. Okay. And yeah, that's it for this problem.